Cosmic nebulae, a single word. Yet it contains within its sound the vastness of space and the profound mysteries of stellar creation. It evokes images of breathtaking beauty, swirling clouds of color, cosmic dust motes dancing under invisible light, ethereal structures reaching across abysses filled with silent gas. And beneath that captivating visual splendor lies a story far more complex, the raw material for stars, the crucible where new worlds are born from ancient gas clouds collapsing under their own gravity. Think about it. Nebulae aren't just pretty pictures, they are fundamental components of our universe's life cycle. They represent periods of calm and chaos, expansion and contraction, birth and death on cosmic scales. Some nebulae are fiery cauldrons where stars are born from collapsing pockets of interstellar material under immense gravitational pressure. Others are the ghostly remnants of stellar explosions, supernovae seeding space with heavier elements forged in their parent stars' hearts. Still others might be cold, dense clouds barely holding themselves together against the pull of gravity, potential nurseries waiting for a cosmic shove to ignite creation. So let's embark on a journey into these cosmic wonders. We'll start by defining what nebulae truly are. Then we can look closer at their different types. The brilliant emission nebulae glowing in hydrogen crimson and sulfur gold. The dark, ominous absorbing nebulae hiding cosmic secrets within their shadows. And the brilliantly reflecting reflection nebulae that catch and amplify the light of nearby stars. We'll delve into how these magnificent structures form. Sometimes, they are simply the leftovers from star formation, expanding clouds of gas flung outwards by newborn massive stars. Other times, like in the case of supernova remnants, they are shockwaves sculpting existing dust clouds with their incredible speed and energy. But perhaps most importantly for this video, we will focus on emission nebulae, specifically the stellar nursery process. How vast clouds of gas collapse under gravity to eventually ignite into stars. This is where cosmic materiality meets stellar destiny, transforming invisible potential into brilliant light across unimaginable distances. And we must remember that these nebulas aren't just about birth. They are also graveyards and recycling factories for older, dying stars. The beauty of nebulae stretches far beyond their immediate visual impact. They serve as laboratories for understanding physics under extreme conditions, gravity's immense power in collapsing gas clouds, magnetic fields shaping flows like cosmic architects, radiation from nearby stars interacting with dense material to create brilliant displays of light. Moreover, nebulas act as time machines. Observing them allows us to glimpse the past and future states of our own sun system. We can see regions where the processes that shaped our solar nebula billions of years ago are still active elsewhere in the Milky Way or other galaxies, witnessing cosmic history repeating itself on a grand scale. The sheer scale of these formations is almost impossible to grasp. A stellar nursery might contain thousands of embryonic stars clustered together within gas clouds, so vast they could stretch across the entire disk of our galaxy, or even beyond structures that appear delicate, yet represent concentrations of mass rivaling planets combined, all held loosely by cosmic forces. This journey isn't just about understanding nebulae, it's a quest to comprehend ourselves. We are born from stardust forged long before our sun and Earth existed within the heart of such a stellar nursery explosion, supernova ejecta seeding the material that clumps together under gravity, eventually becoming complex life like ours on this pale blue dot. So fasten your virtual seatbelt as we explore these cosmic clouds. We'll learn about their nature, their colors, their intricate structures woven from gas and dust threads across the immense backdrop of interstellar space. What is a nebula? Let's define what lies before our eyes in this cosmic tapestry, the nebula itself. A nebula, pronounced nebula, isn't an animal or a plant, nor a geological feature like a mountain range. It's a vast interstellar cloud of gas and plasma, often with traces of dust, existing within galaxies like our own Milky Way. Think of it as a cosmic fog, but far denser than any earthly fog and composed primarily of hydrogen, the most abundant element in the universe. Helium and other elements fused inside stars during their lifetimes. These gases are incredibly spread out, think thousands of times less dense than Earth's atmosphere at its thinnest points. A nebula forms when concentrations of these gases become high enough to be visible against the backdrop of interstellar space, or because a bright star is illuminating surrounding dust from within. These clouds aren't static. They evolve and change over cosmic timescales, often millions or billions of years. They can range in size from relatively compact structures just a few light years across, roughly equivalent to a small stellar cluster, to colossal expanses stretching for tens, hundreds, or even thousands of light years. Imagine observing one from Earth. It might appear as an immense cloud with distinct boundaries and internal structure, glowing brightly under its own emission or reflecting nearby starlight. Or you might see just a dark patch obscuring the bright stars behind it. That's an absorbing nebula, also known simply as a nebula in many contexts until observed closely. The term originates from historical usage by astronomers like William Herschel in the 18th century, who catalogued these diffuse patches on the sky. Later, with more advanced telescopes, we realized they encompass various types of clouds and phenomena. Understanding nebulae requires looking beyond simple definitions to grasp their complexity as structures sculpted by cosmic forces: gravity, radiation pressure from nearby stars, magnetic fields, invisible lines stretching across vast distances that influence charged particles, and even the motion of gas within them. Types of nebulae. Emission nebulae. Deeper dive. Not all nebulae look like or behave like glowing clouds. Their appearance depends on their composition, density, temperature, and interaction with surrounding light sources, often stars themselves. One prominent type we aim to understand is the emission nebula. Emission nebulae, sometimes called H-2 regions after the most common element they emit, hydrogen, glow brightly by emitting visible light through fluorescence. Think of it like a special kind of cosmic paint. Invisible energy absorbed from nearby starlight or other sources excites gas atoms within the cloud, causing them to jump between different states. When these excited atoms return to their normal state, they release photons, tiny packets of electromagnetic radiation we perceive as specific colors of light. This process is what makes emission nebulae so visually stunning. Their characteristic colors aren't randomly generated. They are a direct result of the physical processes happening within them and the types of atoms present. Hydrogen gas, H, emits red light when its electrons transition from one energy level to another. This specific wavelength is famously seen as part of the pinkish hue in many nebulae, especially prominent ones like the Trifid Nebula or the Crab Nebula's colorful regions. However, it isn't just hydrogen creating these spectacular colors. Heavier elements play crucial roles too. Sulfur, chemical symbol S, emits light at various wavelengths within emission nebulae. One common type is seen around 10.5 micrometers, a mid-infrared wavelength invisible to optical telescopes like ours, but detectable by instruments designed for that part of the spectrum. This sulfur emission often appears red in visible light images because we're seeing fluorescence at longer wavelengths where dust absorption is minimal. Nitrogen, N, another key element, can produce blue-green emissions. Think bright turquoise colors sometimes seen in nebulae like NGC 246 or parts of the Swan Nebula, IC 18.5. These emissions are usually observed in visible light spectroscopy rather than direct photography. Other elements contribute vibrant hues. Oxygen typically produces a very bright green emission, often one of the most striking colors in young stellar nurseries. Carbon can also emit green light, adding another layer to this cosmic palette. Iron might show up as yellow or orange lines against dark backgrounds. These elemental paints, hydrogen crimson, sulfur gold and ruby red, oxygen emerald green, nitrogen azure, combine within the nebulae to create breathtaking visual tapestries that span thousands of light years in our own galaxy alone. The process isn't just about element emission. Ionized gas plays a key role. Stars don't simply glow randomly onto their neighbors. They can ionize vast amounts of surrounding hydrogen gas by constantly emitting photons, invisible particles of energy, with enough power to strip electrons from neutral hydrogen atoms, turning them into electrically charged plasma. This process is crucial because it's the plasma that carries electricity and magnetic fields across space, influencing how gas falls onto a potential protostar or forms distinct structures within the nebula itself. Stars themselves are often embedded deep within these clouds. The ionizing radiation from massive young stars, protostars still in their earliest stages, can penetrate surrounding dust layers, creating glowing shells of excited hydrogen gas visible against dark regions. This interplay between light emission and gravitational collapse defines a stellar nursery, the cosmic cradle where vast amounts of neutral molecular cloud material begin transforming into something more profound. Individual stars with distinct masses and potential lifespans. The resulting structures aren't just pretty colors. They are complex entities shaped by turbulent flows, magnetic fields guiding gas streams like invisible ropes holding matter together against its own tendency to disperse. Birth of stars in nebulae. Now we can focus on the most awe-inspiring aspect of these cosmic clouds, their role as stellar nurseries. Stars aren't eternal sparks, they have a beginning. Our sun didn't just pop into existence billions of years ago without cause. It formed within an interstellar cloud, likely similar to those bright emission nebulae we saw earlier but much denser and in a different evolutionary stage. This process is fundamental to the cosmic cycle. Gravity pulling material together from vast expanses eventually leads to ignition points where new stars are born. Imagine gas collapsing under its own weight. This happens everywhere. Gravity constantly tugs on everything, even across empty space. But interstellar clouds aren't uniformly structured like a fluid. They consist of tiny clumps within the diffuse background material. These dense cores collapse faster than their surrounding shells because gravity pulls more strongly towards them. As these cores shrink and heat up under immense pressure, equivalent to thousands of Earth atmospheres squeezed onto itself over vast timescales, they become protostars. These newborn stars are still very inactive compared to their final state after nuclear fusion ignites. They haven't started burning hydrogen yet, which provides the actual energy for stellar shine. Instead, massive protostars, those several solar masses or more, constantly emit powerful ultraviolet photons capable of ionizing surrounding hydrogen gas and creating those glowing emission nebulae we adore. So, an emission nebula isn't just a cloud. It's often the visible glow shed by newborn massive stars hidden within their collapsing birth clouds. This process, a star forming within its own glowing remnant envelope, is why these regions are called stellar nurseries. The beauty of this process lies not only in its visual manifestation, but also in its complexity. Observing nebulae allows astronomers to witness the very early stages of star formation, which rarely occur close enough to Earth for direct study otherwise. These observations provide crucial data about how stars themselves build up their mass from surrounding dust and gas, a fundamental question explored through these cosmic phenomena. We see giant molecular clouds, dense cores, forming within vast nebulae complexes. These clouds are the raw material reservoirs containing all the necessary elements: hydrogen, helium, carbon, oxygen, nitrogen, and trace amounts of heavier metals essential for planet formation. Within them, gravity drives collapse, leading to the formation of protostars embedded deep inside dense cores, often shielded from our view by surrounding glowing gas. The process isn't smooth. Magnetic fields can halt collapse temporarily or guide collapsing streams along specific paths like cosmic highways. Radiative feedback from massive stars, intense radiation fields that can disrupt nearby cloud material, preventing further star formation unless the gas is sufficiently protected, adds another layer of complexity to these stellar cradles. Protostars evolve through different phases. Some might form directly into main sequence stars, the stable phase where hydrogen fusion occurs in their core, like our Sun. Others, much more massive ones, will undergo rapid collapse and ignite nuclear burning prematurely, becoming what we classify as B-type stars or similar, but perhaps evolving differently due to higher mass effects. Protostars are essentially gravitational engines. they don't convert matter into energy via nuclear fusion yet. That process relies on the immense pressure created by their own gravity compressing material over time. This continuous collapse provides heat until temperatures reach millions of degrees Celsius, triggering hydrogen fusion in a stable shell or directly within the core for higher-mass protostars. The resulting stars then clear themselves further by expanding and emitting more light, becoming T-Tauri stars initially, later evolving into luminous Herbig I/B stars for stellar masses several times our Sun's, as they shed their surrounding envelopes. This entire process of gravitational collapse, accretion onto a protostar core, ignition via nuclear fusion, and subsequent clearing defines the birth of stars within nebulae complexes, a cycle that repeats across galaxies and throughout cosmic time. Dark nebulae, absorbing the light so far, our journey has focused on glowing clouds. But what about those dark patches that often appear in astronomical photographs? They are crucial components of the cosmic landscape. We encounter absorbing nebulae, commonly called dark nebulae, when dense dust clouds block out light from background stars or galaxies. These aren't truly empty space. Rather, they are clumps of material so concentrated that visible light struggles to penetrate them. Think of dark nebulae as cosmic silhouettes, islands of darkness floating within the vast ocean of starlight. Their density is high enough, typically several times Earth's atmospheric density, for dust particles and gas to absorb incident radiation effectively, preventing it from reaching our eyes. Dark nebulae are often depicted in stunning contrast shots. Imagine a bright field starry background abruptly cut off by sharp dark boundaries. These aren't just artistic choices. They represent the physical reality of obscuring material blocking light. Sometimes, we see elongated dust clouds silhouetted against glowing emission nebulae or planetary nebulae, briefly mentioned later, like the Horsehead Nebula famously contrasting with the bright starlight from Orion's belt. The term dark nebula isn't very descriptive of their immense size. These aren't tiny pockets. They can stretch for many light years, forming dense cores within larger molecular clouds. Their presence is vital because it shields underlying material, preventing it from being ionized prematurely by nearby bright stars, like those in emission regions, and allowing gravitational collapse to proceed relatively undisturbed towards star formation. This shielding effect protects the protostars forming within them until they develop enough self-luminosity that their own light can escape the surrounding dense material. Without dark nebulae, vast concentrations of gas might never collapse or could be prematurely disrupted by ionizing radiation fields from nearby massive stars in an adjacent emission region. Their composition is similar to other interstellar clouds, primarily hydrogen and helium with heavier elements. The key difference lies in density, significantly higher than typical diffuse interstellar material. This dense material provides the gravitational potential needed for collapse, while simultaneously blocking light effectively. Observing dark nebulae requires specific conditions or equipment. Many are best viewed through long-exposure photography that captures faint details against a darker sky background, especially useful near galactic centers. Or they can be studied using infrared observations which penetrate dust better than visible light. This hidden reservoir of potential star formation underscores the complexity and layered nature of nebulae themselves, acting as both protectors and facilitators for cosmic rebirth. Reflection nebulae. Catching the light, another visually distinct type of interstellar cloud, is the reflection nebula. How does it differ from absorbing or emission types? Instead of emitting its own light through fluorescence, a reflection nebula simply reflects starlight. Its visible glow comes not from internal heating, but from the scattering of blue light, similar to Earth's Rayleigh scattering causing blue skies, off tiny dust grains embedded within its cloud structure. These dust grains act like cosmic mirrors, catching and redirecting photons towards our telescopes or other observers. Think of it as looking at a bright lampshade made of reflective material, but in space. Typically found surrounding newly formed stars, Class 1 and Class 2 protostars. These dense clouds are illuminated by their own gravitational engines that are still contracting and heating up, making them intrinsically bright sources. The dust grains absorb blue light more effectively than red due to their composition. Think of tiny tholins or other carbonaceous materials coating the particles. So the scattered light we see tends to be bluish. This gives reflection nebulae a characteristic cool, often strikingly blue appearance that contrasts beautifully with surrounding warmer emission nebulae glowing in crimson. A classic example is the nebula surrounding the bright star Bellatrix within Orion's belt. This region appears distinctly blue against the backdrop of red hydrogen gas and other structures. These nebulas are often associated with multiple processes, not just reflecting light, but sometimes also scattering it via fluorescence depending on specific dust types or cloud conditions. Observing reflection nebulae requires clear lines of sight to their illuminating stars. Because they don't generate their own visible light from internal heating, like emission nebulae do, the primary source must be unobscured. This makes them dynamic indicators of ongoing star formation, often appearing brightly when a massive protostar ignites in its vicinity. Their structure is typically denser than diffuse reflection material. Often, they form distinct shells around newly ignited Herbig I/B stars or other luminous young stellar objects, YSOs. Planetary nebulae brief stages for intermediate mass stars transitioning into white dwarfs also display reflection nebulae properties because the dust shell surrounding them scatters light effectively. The presence of a bright reflection nebula often indicates intense mass loss from its parent star during early development. This is important feedback that affects surrounding cloud material and potentially hinders further collapse unless carefully shielded. Overall, reflection nebulae contribute another beautiful facet to the cosmic nursery scenes, their blue glow acting as an essential counterpoint to the fiery emission regions and serving as a marker for stellar activity deep within clouds. Diffuse nebulae, the vast environment so far, we've talked about relatively dense clouds. But remember that nebulae exist on vast scales. Many interstellar clouds appear very diffuse, almost transparent to optical light, but still significant in mass and structure across immense volumes of space. These are often classified as diffuse emission nebulae, or simply diffuse nebulas. They can be enormous, extending over hundreds of thousands of square degrees, an area covering vast portions of the night sky from our relatively distant vantage point on Earth, yet still contain noticeable amounts of glowing gas plasma. Their low density makes them challenging to observe directly, often detected through long-exposure photography or by analyzing their faint spectral lines, invisible fingerprints left by ionized elements within them. These diffuse clouds represent transitional phases between the dense molecular cores that collapse into stars and the near-vacuum background interstellar material, which is still present but incredibly sparse. They can be remnants of supernovae explosions long past, forming large shell structures around stellar clusters or galactic centers. Or they might be regions where ionization fronts, boundaries created by intense ultraviolet radiation from newly formed massive stars pushing into neutral hydrogen gas clouds have occurred. These frontiers mark the interface between glowing plasma and invisible molecular hydrogen, often appearing as faint blue-green filaments in sensitive observations. Diffuse nebulae aren't just passive. They can influence star formation through gravitational effects or by providing a reservoir of material that slowly settles onto denser cores over cosmic time. Their presence shapes the large-scale structure of galaxies themselves. They also play roles during galactic evolution, being swept up into spiral arms as part of turbulent gas flows, fueling subsequent bursts of new star birth within those preferred locations. Sometimes these diffuse clouds can be actively forming clusters of stars through gravitational fragmentation or turbulence rather than isolated stellar nurseries. The process is complex and interrelated on cosmic scales. Diffuse nebulae act as the vast sea, into which dense pockets drift and interact, creating a dynamic environment where star formation potential arises constantly from turbulent mixing. Understanding diffuse nebulae requires appreciating their role within the larger galactic ecosystem, not just as beautiful or hideous phenomena, but as key components in building our universe's structures over billions of years. Their subtle presence highlights how pervasive these cosmic processes truly are, shaping even the seemingly empty spaces between stars into integral parts of a vast, interconnected system. Nebulae as stellar nurseries. Density and structure for a nebula to serve effectively as a stellar nursery, triggering star formation through gravitational collapse and providing material for ignition, it must possess certain physical properties. Primarily, density. While emission nebulae need high enough densities, often above 100-200 particles per cubic centimeter, to glow brightly under ionizing radiation, the surrounding dark or reflecting regions often have much higher densities. Typical molecular cloud cores where stars are born can reach densities vastly exceeding these thresholds, sometimes reaching values thousands of times denser than typical emission nebulae. This is measured in millions of particles per cubic centimeter near active collapse zones. This extreme density provides the necessary gravitational pull to overcome thermal pressure and magnetic support, allowing material to gather into compact objects. But structure matters just as much as simple density numbers. A cloud must be stable enough initially against turbulent gas flows or stellar winds pushing it apart before collapse can proceed effectively towards star formation. Think of a nebula as having internal clumpiness, dense pockets embedded within the larger diffuse background that are prime candidates for gravitational engine ignition. These structures aren't random. They often form via self-gravity gathering material together, perhaps amplified by shockwaves or magnetic fields acting like cosmic ripples. This creates hierarchies, small cores building into clusters of protostars. Imagine observing a vast nebula complex, seeing not just one star-forming region, but potentially multiple dense knots actively collapsing and evolving independently. The interplay between density and structure dictates how quickly collapse occurs, what types of stars eventually ignite from the process. Massive O/B-type stars versus lower-mass red dwarfs, and whether feedback mechanisms like radiation or stellar winds halt further formation within that area. This complex dance defines the cosmic nursery environment, where order emerges from chaos over incredibly long timescales. Furthermore, the presence of heavier elements, metals in astronomical terms, influences how efficiently gas collapses under gravity. Metallicity affects thermal properties, radiation absorption versus emission, and dust opacity, blocking light effectively, but also absorbing energy crucial for heating. This balance between transparency to radiation fields needed to start glow emission processes versus effective shielding against premature disruption by ionizing photons is critical. Therefore, a stellar nursery isn't just one nebula. It's often multiple interacting types. Dense dark cores feeding bright reflection regions surrounding newly ignited protostars that are then powered as emission nebulae once their intense ultraviolet radiation clears the surrounding material. The process involves continuous feedback loops between forming stars and the gas/dust, environments they inhabit shaping both the stellar population within a cluster and the vast cosmic structures where it occurs. Shocks and magnetic fields. Sculpting the cosmos so, gravity isn't the only actor in shaping nebulae. In fact, its influence alone might not be enough to create such complex structures like emission nebulae or even dense cores. Other forces play crucial roles, perhaps none more dramatic than shockwaves and magnetic fields. Shockwaves occur frequently within stellar nurseries. They are generated by various mechanisms. Fast-moving jets expelled from newly ignited protostars, Herbig I/B stars, T-Tauri stars, powerful stellar winds from massive stars nearing the end of their main sequence life, pushing into surrounding dust clouds at supersonic speeds, sometimes reaching millions of kilometers per hour relative to local gas. Or they can be remnants of past supernova explosions or even galactic collisions where vast amounts of interstellar material are rammed together, creating turbulent conditions and shock-heated gas across enormous regions. These shocks aren't gentle caresses, they're violent disturbances. Imagine a powerful gust of wind hitting an obstacle. The air gets compressed and heated downstream. Similarly, within nebulae, shockwaves accelerate gas to high velocities along specific paths or boundaries. They can compress surrounding material dramatically, increasing density enough for gravitational collapse to proceed more rapidly. Think of it as gravity working on a longer timescale, over millions of years potentially, while shocks operate much faster, creating immediate changes and sculpting intricate details within the vast cosmic canvas. For example, many organic shapes seen in nebulae photographs are actually the results of complex shock interactions. Filamentary structures, knots, pillars, expanding shells. These often owe their existence to shockwaves carving out specific patterns. But magnetic fields also play a fundamental role. Invisible lines stretching across vast distances, sometimes thousands or even millions of kilometers long within a single galaxy's interstellar medium, exert powerful control over charged particles. The gas cloud material contains ionized atoms, and dust grains carry electric charges influenced by these ambient magnetic fields. This creates a dynamic equilibrium. Gravity wants to collapse the field structure. Magnetic pressure provides outward support. Depending on which force dominates locally or regionally, different structures form. Think of galaxies themselves. Spiral arms might be maintained in part by magnetic field pressures interacting with gravitational pull. On smaller scales, within nebulae complexes, magnetic fields can guide collapsing gas streams along preferred paths, acting as cosmic highways for stellar assembly. They can also channel star formation into dense clusters rather than smooth sheets, creating distinct concentrations where gravity and magnetic forces align. The interplay between these invisible forces, gravity, magnetism through plasma physics, and the kinetic energy deposited by shocks, is complex. It shapes not just the final appearance of nebulae, but influences the very process of star formation itself. Observations across different wavelengths help decipher this cosmic puzzle. Radio waves show neutral hydrogen gas structure. Mid-infrared reveals dust emission and heating patterns. Optical shows glowing gas filaments under fluorescence or reflection processes. Each observation gives a slightly different view, helping us understand how gravity, shocks, and magnetic fields collaboratively sculpt the landscapes where stars are born. The universal significance of nebulae. We've been focusing on nebulae within our own Milky Way galaxy. But these aren't exclusive to single galactic systems. Nebulae exist throughout the vast cosmos, in every spiral arm of distant galaxies, within elliptical galaxies whose stellar populations might be more dispersed, and thus lacking dense cloud structures, though some remnants still exist. Across intergalactic voids where occasional gas clouds drift under immense gravitational influence from galaxy clusters. The same physical processes that create nebulae here are operating elsewhere. Gravity collapsing material, radiation fields interacting with dust, shocks shaping boundaries. This universality means we're not just observing one phenomenon, but glimpsing the cosmic engine itself in action across different environments and evolutionary stages. Confirming the fundamental principles of stellar physics extend beyond our immediate galactic neighborhood. Perhaps most importantly, nebulae act as time capsules for our own Milky Way's history. Observations within nearby star-forming regions, like Ophiuchus or Taurus, show processes similar to those believed to have occurred in early solar system evolution. But by looking at emission nebulae in other galaxies, especially younger ones still forming significant amounts of new stars, we see potential future states for our own galactic environment. Conversely, studying older stellar populations within the Milky Way involves identifying regions where star formation ceased long ago. These often mark depleted molecular gas reservoirs or areas now dominated by evolved stars and their remnants. Nebulae themselves can be ancient objects if they represent supernova shells from past generations, but active emission nebulae clearly point to ongoing processes. They provide context for understanding how galaxies form and evolve over cosmic time scales. Active star formation zones within a galaxy often correlate with areas of higher dust content regions, where gas clouds are dense enough to collapse under gravity into new stars. This process releases gravitational potential energy, heating surrounding material through shocks or stellar winds, creating feedback that can halt further expansion in some areas while fueling others. Moreover, the heavy elements, metals, fused inside dying stars within these nebulae are essential for planetary formation and complex chemistry necessary, perhaps even for life on habitable worlds. Observing nebulae is therefore witnessing not just star birth, but also cosmic recycling, the return of vital materials to the interstellar medium after stellar lifetimes end. In essence, studying nebulae isn't just about beautiful pictures. It's a key step in understanding our own place within this vast cosmic ecosystem. We are made from stardust forged long ago in such processes. We'll continue now by exploring how these magnificent structures can be observed and studied using various telescopes, revealing hidden details across the electromagnetic spectrum. Observing nebulae. Across the spectrum, nebulae aren't visible only through optical, visible light telescopes. Their complexity requires looking at different wavelengths to fully appreciate their nature. Each type of telescope reveals a unique aspect of these cosmic clouds because they interact differently with various forms of radiation, from radio waves up to gamma rays. First, consider the most common view. Colorful emission nebulae like those in Orion or the Eagle Nebula M16. Their stunning visuals come primarily from visible light fluorescence and reflection processes. But powerful ultraviolet emissions from hot gas atoms also occur, invisible to our eyes yet detectable by specialized telescopes. This UV glow provides crucial information about recent star formation activity. Infrared observations are particularly valuable for studying nebulae in detail. Many cold dust clouds responsible for shielding protostars don't glow brightly in visible light, but heat up slightly under stellar radiation or cosmic microwave background influence, emitting thermal infrared radiation. This allows telescopes like Spitzer Space Telescope or the James Webb Space Telescope to peer through dense layers of gas and reveal hidden structures, young stars still deeply embedded before they clear themselves with emission processes. Mid-infrared wavelengths can show dust grains absorbing energy from nearby starlight or emitting their own heat, providing a thermal map of the cold reservoirs within glowing regions. This is vital for understanding how material cycles between dense cores, potential sites, and diffuse gas reservoir. Radio telescopes offer another unique window. They detect neutral hydrogen atomic HI regions. While not all nebulae contain significant amounts, radio observations can reveal vast quantities of this primordial component extending across enormous areas. The 21 cm line, a specific wavelength associated with neutral hydrogen hyperfine transition, is often used to map large-scale gas distributions undetected by optical telescopes. Molecular lines observed via radio telescopes, like carbon monoxide, ammonia, or other heavier molecules, indicate the presence of cold, dense material ideal for gravitational collapse into stars. This helps pinpoint areas where star formation might be occurring even without visible emission nebulae yet clearly established. X-ray observations can reveal high-energy processes associated with nebulae. These include protostellar jets interacting with surrounding gas, creating shock-heated plasma flares, accretion disks swirling around protostars, especially those forming close to stellar cores, emitting intense X-rays as material spirals inwards, remnants of past supernova explosions where hot gas is still expanding and cooling slowly. Gamma rays might also be detectable from the most violent processes, perhaps neutron star mergers or other extreme events, but less commonly associated directly with typical nebulae formation outside active galactic nuclei, AGNS. Each observational window provides a different piece of the cosmic puzzle. Combining data from optical telescopes showing glowing shells, radio telescopes mapping neutral gas clouds and cold dust structures, infrared revealing warm dust emission or embedded stars, and X-ray detecting high-energy processes allows astronomers to build comprehensive models. Nebulae as laboratories for physics. Perhaps one of the most fascinating aspects of cosmic nebulae is their function as natural laboratories for extreme physics research. These aren't controlled environments on Earth. They are unique phenomena where forces like gravity acting over astronomical scales, magnetic fields influencing vast amounts of charged matter across light years, and radiation fields exceeding anything we can produce here interact freely in a vacuum. Imagine trying to replicate stellar formation conditions in a lab. It's impossible with current technology. The temperatures involved reach millions of degrees Celsius. The pressures vastly exceed Earth's atmosphere. Gravity works over scales far beyond our capabilities. Yet, within nebulae complexes like Orion Nebula or NGC 346, we observe these exact processes happening constantly. Studying emission nebulae provides direct insight into ionization processes. By analyzing their spectral lines, specific wavelengths associated with glowing atoms of different elements, hydrogen H-alpha line around 656 nm in visible light, sulfur SMINUS-2 and SMINUS-3 lines at longer infrared or even radio wavelengths. Scientists measure gas temperatures, densities, velocities within the cloud. This data helps verify models for how stars emit photons during their formation phase via ionizing radiation fields. Reflection nebulae offer opportunities to study dust properties. The specific ways blue light scatters off tiny grains tells us about grain size distributions and chemical composition using polarimetry. This connects back to heavy element production in previous generations of massive stars, a direct link across cosmic time. Observing these scattering effects also reveals how dust influences light propagation across vast distances. Dark nebulae, with their high density, allow researchers to study gravitational collapse physics at work. Observing the shape and speed of collapsing clumps provides clues about mass accumulation rates and timescales for forming protostars, information critical for understanding stellar birth statistics. Their role in shielding underlying processes from disruption by ionizing radiation is another key area of investigation. Furthermore, nebulae help study galactic evolution itself. By comparing different regions within a single galaxy, like the bar versus spiral arms, or across various galaxies at different stages of development, scientists track how star formation activity correlates with large-scale structure over time. This provides constraints on cosmological models describing the overall expansion and cooling history of the universe. Shockwaves in nebulae are excellent examples for studying magnetohydrodynamics, MHD. How does fast-moving plasma interact with slower gas under magnetic field influence? This complex physics governs everything from aurora borealis phenomena to cosmic jets sculpting their surroundings. Nebula observations help refine our understanding of these fundamental interactions. Therefore, beyond being beautiful sights in the sky, nebulae are active testbeds where theories about gravity, electromagnetism, through charged particle interactions, nuclear fusion ignition mechanisms, and even dark matter distribution can be challenged or confirmed against reality. Their study is paramount for advancing our knowledge of the cosmos's underlying physical principles. The enduring legacy of stars, debris and recycled matter. While we focus on star birth in nebulae complexes today, remember that these clouds also represent potential graveyards and recycling factories for older stars. We mentioned dark nebulae shielding formation, but they can also be remnants. Consider planetary nebulae, beautiful shells of glowing gas expelled by intermediate-mass stars nearing the end of their life cycle. These are essentially expanding envelopes, similar to the surrounding young Herbig I/B stars or T-Tauri stars, but from a much older star. The central remnant is typically an exposed hot core, now acting more like a protostar in its final stages before igniting stable hydrogen burning, the main sequence phase, at very high temperatures and pressures. This stellar debris forms because as these aging sun-like stars exhaust their hydrogen fuel, they expand into red giants or supergiants. During this expansion, powerful stellar winds push out the outer layers of gas and dust similar to what happens in young stellar objects, creating reflection nebulae phases. Sometimes this mass loss is triggered by internal nuclear burning processes changing dramatically near the end of life. The expelled material then forms a distinct shell that glows brightly under ionization from the hot central remnant. This is precisely where planetary nebulae get their name, because they look similar to diffuse reflection nebulae, but are much closer and more compact, often extending for light years, while typical dark absorption nebulae might be similarly sized. These shells aren't permanent. They gradually expand away from the stellar cluster, cooling down over time until the gas disperses completely back into interstellar space. Eventually, this recycled matter mixes with other cloud components. But their beauty is undeniable. Think of the famous Dumbbell Nebula, NGC 694, or the Cat's Eye Nebula, a more complex example showing intricate structures. And beyond planetary nebulae, what about supernova remnants? These are massive shells created when a very large star exhausts its fuel and detonates catastrophically, blowing itself apart in an unimaginable explosion. These events create even larger nebulae complexes than stellar nursery stages typically do. The shockwave from the blast expands outward at nearly relativistic speeds, probing galaxies as cosmic pressure waves, heating gas behind it to millions of degrees. The resulting emission comes not from internal fluorescence, but primarily from thermal Bremsstrahlung, hot charged particles radiating energy through their interactions with surrounding magnetic fields. These are short-lived phenomena compared to stellar nurseries, lasting perhaps thousands or tens of thousands of years before cooling down and dispersing into galactic gas clouds once more. Yet, they leave a crucial legacy, seeding the interstellar medium with heavy elements, carbon, oxygen, nitrogen, iron, synthesized in the star's core during its lifetime. This recycled material becomes part of future generations' molecular clouds, shaping not just stellar populations, but potentially enabling planet formation and complex organic chemistry elsewhere. Therefore, nebulae aren't exclusively scenes of creation. They also represent endings, recycling processes, and the continuous circulation of matter within galaxies. Their existence depends on previous star deaths. This cycle is fundamental. Birth right arrow, death right arrow. New cycles begin with recycled material or leftover debris from failed ignition attempts, like supernova remnants. So we're witnessing a cosmic conveyor belt, material constantly cycling through various stages across emission, dark absorption, reflection nebulae types, and stellar remnant categories. It's an interconnected system that defines galactic evolution itself. The wondrous diversity of cosmic nebulae, one of the most captivating aspects of studying interstellar clouds, is their sheer diversity in form, structure, and appearance. From relatively simple glowing gas regions like diffuse emission nebulae to complex clusters containing hundreds or thousands of protostars embedded within intricate dust structures. The shapes are endless. Let's expand our view further. We've seen prominent emission nebulae like the Trifid Nebula Mate, which combines multiple types: glowing hydrogen, reflecting dust illuminated by a bright young star cluster at its heart, and absorbing material obscuring parts of it from direct view. Classic examples like these help define what we expect to see. But consider more complex structures. Filamentary nebulae stretch across vast distances. Think of the Crab Nebula's filamentary patterns or giant molecular clouds, themselves sometimes exhibiting elongated shapes under magnetic field influence rather than collapsing isotropically, in all directions equally. Bowl-shaped cavities are another common feature, often sculpted by stellar winds from clusters pushing outwards into surrounding gas and dust. These bowls can eventually become sites for new star formation if dense cores form along their edges. Or consider the vast pancake-like nebulae supergiant shells, sometimes seen in regions like 30 Doradus within the Tarantula Nebula, part of a larger system near the Large Magellanic Cloud. These might be associated with expanding supernova remnants or galactic collision debris. Then, there's the shark fin shape mentioned earlier, likely created by outflows from protostars perpendicular to magnetic field lines, pushing gas away and revealing bright emission regions behind them. This highlights how geometry itself plays a role in nebula evolution. Nebulae aren't always uniform either. They often consist of multiple distinct components layered or embedded within each other over time, creating hierarchical structures visible even across light-year scale gaps from our observation point on Earth. Observing these requires sophisticated techniques like adaptive optics, correcting telescope blur distortions induced by atmospheric conditions, to resolve fine details, or combining data from many telescopes for complete picture assembly. The colors also vary dramatically. While hydrogen often provides a base red tone, other elements add unique hues: oxygen green, nitrogen blue-green, sulfur ruby red or yellow gold depending on the specific ionization state and observational method. Sometimes even carbon contributes; its emissions appear bright in mid-infrared wavelengths, but might look like hot spots under certain conditions. Moreover, different phases within a single stellar nursery complex can display vastly contrasting colors. Hot gas shells near newly formed stars burn intensely. Cooler dust regions reflect bluer light from the same source or appear redshifted due to thermal glow mechanisms. This rich tapestry of color provides clues about temperature gradients and internal processes operating within the cloud. Therefore, each nebula presents a unique puzzle. Its configuration tells part of the story of how it formed, evolved locally, and interacted with surrounding galactic structures over time. No two are identical. They all tell their own cosmic tale through their intricate shapes and diverse colors. The role of interstellar dust. While gas dominates many discussions about nebulae, especially in emission regions, don't forget the crucial role played by dust. Interstellar dust consists of tiny grains, microscopic flecks typically made from carbon, silicates, or other heavy elements floating within vast cosmic clouds. Its presence profoundly affects light propagation and overall cloud physics. Think of it as an incredibly thin curtain between stars. Dust grains absorb some wavelengths more effectively than others. In particular, they strongly absorb blue starlight, causing the familiar reddening effect where background objects appear redder because their blue component is filtered out by intervening dust clouds. This helps explain why reflection nebulae often look bluer than expected, because dust scatters light efficiently in those specific wavelengths. But more importantly, dust provides surfaces for gas molecules to adhere and potentially react. The chemistry within dense cores where stars form likely involves catalytic reactions on dust-grained surfaces that wouldn't occur otherwise. This facilitates the complex cooling mechanisms needed during gravitational collapse before nuclear ignition occurs, transferring heat via surface interactions, rather than relying solely on internal plasma processes. Dust also acts as a shield against ionizing radiation, protecting underlying gas from premature heating or destruction, until stars themselves ignite enough to counteract these effects through their feedback, e.g., stellar winds. It influences the balance between gravity and pressure in collapsing cores, making dense pockets more likely by concentrating mass slightly due to dust grain inertia. Furthermore, observing dust directly is difficult. It appears dark against bright backgrounds because of absorption, but its presence can be inferred indirectly when we see sharp boundaries contrasted sharply with brighter emission nebulae, like the Horsehead Nebula, blue scattering reflection regions pointing back towards dense foreground material, dark patches, obscuring otherwise visible stars or galaxies. These observations tell us about dust density and distribution patterns, crucial parameters for models of star formation feedback cycles. In summary, interstellar dust isn't just a passive component adding texture. It's an active player shaping the very physical processes occurring within nebulae complexes. Its complex interactions with gas determine how efficiently stars ignite from collapsing material. Conclusion: the beauty and power of cosmic nebulae. Our journey through the world of cosmic nebulae has taken us across different scales, wavelengths, and physical mechanisms, revealing a universe teeming not just with individual stars, but entire ecosystems governed by gravity, radiation pressure, magnetic fields, and complex chemistry involving dust. From a mission nebulae catching the invisible energy from newborn massive stars to reflect brilliant colors like crimson or ruby red against dark galactic backdrops. These are scenes of ongoing creation. We saw how they form the crucial birth sites where collapsing gas clouds transform into stable luminous objects with distinct lifespans, emitting unique patterns and elemental fingerprints across different observational windows. Then we explored supernova remnants as cosmic pressure waves expanding outwards from stellar detonations, seeding galaxies with heavy elements essential for planetary formation elsewhere. We considered how dark nebulae shield underlying processes from disruption by ionizing radiation, allowing gravitational collapse to proceed even in dense environments, where simple optical observations might show nothing but hiding potential star birth sites effectively. The sheer scale and diversity of these structures, their ability to evolve dynamically over millions or billions of years, while simultaneously providing a snapshot frozen in time through specific observational methods, showcases the immense complexity packed within seemingly empty interstellar space. They aren't passive. They are active participants driving galactic evolution forward, from star formation ignition points deep inside dense cores to recycling vast amounts of matter into new configurations across cosmic landscapes. So whether viewed as pure beauty through colorful emission processes or recognized for their fundamental role in building stars and galaxies via complex physics interactions, cosmic nebulae remain central figures connecting the past, present, and future states of our universe. Their study continues to astound and challenge astronomers with intricate structures that seem almost impossible under known physical laws, yet occur constantly across the cosmos.